Next we have Theodora talking about ancient solutions to meet curvature flow. Thanks, Theodora.
Thank you for the invitation to speak here. Yeah, so let's talk about ancient solutions to mean curvature flow. So to start the setting, we have a family of hypersurfaces. We say that it satisfies mean curvature flow if these hypersurfaces, they move by their mean curvature. Because I'm going to use X as a parameterization of the hypersurfaces, and I'm going to call MT the slices. And in the special case of dimension 1, we call the flow curve shortening flow. Okay, in that case, our speed is just a curvature. Now, as we've heard a lot in this meeting, the big problem of mean curvature flow is that the mean curvature doesn't necessarily stay finite. It might blow up. And in that case, we say that the flow develops a singularity. And the standard examples are the cylinders and the spheres, where we know that when the curvature goes to infinity, everything disappears. But there are cases like the neck pinch, which is drawn in this picture. Well, we have a dumbbell that pinches in the middle, the curvature goes to infinity, but you still have some surface. And mean curvature flow satisfies the avoidance principle that says that if you have two surfaces that are, or hypersurfaces that are disjoint, then they should remain disjoint throughout the flow. And using this, there are ways that you can show that these singularities occur. Okay, so for example, like in this picture here at the bottom, this is taken by Klaus's book. This shows how you can put spheres inside the dumbbell and a conical configuration outside to show that something has to happen in the neck. Okay, so when we want to study the singularities of mean curvature flow, as Natasha also said, what we do is we blow up around the point where the curvature goes to infinity to study these high curvature regions by zooming in our space-time at that point. So when we do this, what we get as the limit is again a mean curvature flow, but this has a special property that it existed for all time in the past. And we call this flows ancient flows. Okay, so ancient solutions, they model singularity of mean curvature flow, and therefore they are of interest to classify. Okay, so the big question is to classify all of them. Of course, like there's no way we can do this so generally, so we start imposing geometric conditions. And we've already seen that convexity is a natural condition, because convex ancient solutions, they appear, the model singularities of mean convex mean curvature flow. So we're going to focus on convex ancient solutions, and whenever I will have a compact one, I would assume that we have translated time so that the surface disappear at time t equals 0. Okay, it is known as a theorem of Pushkin that says that if you have a convex compact solution, then this under the flow, it would become more and more spherical and disappear at a round point. Okay, so special case of these ancient solutions are the solid solutions, solutions that move purely by symmetries of the equation. And we can get this when we do this rescaling. If we do this in a proper way, then we can get the solid solutions. And there are two main ones. There are the shrinkers that change by dilation in time, and the translators that are, they just translate in time. Okay, so let's see some examples. So the major example in curve shortening flow is the Grim Reaper. So the Grim Reaper is a translating solution, and it is given by the graph of the function x goes to minus log cos x. Okay, so this is an example of a convex translator, non-compact, a convex non-compact ancient solution, and it is confined between two parallel lines of width pi. Now there is a very a solution which is very close to the closely related to the Grim Reaper, that is the Angenat oval. And this is a solution, again, between two parallel lines. Is given by the equation cosine x equals e to the t hyperbolic cosine y. And this is a solution that, as we let t go to minus infinity, in any compact region, we're just going to see two parallel lines. Whereas if you look at the tips, yeah. So when we look at the tips, so this region here, if I translate the tip at the origin and I let t go to minus infinity, then I'm going to see the Grim Reaper as the limit as t goes to minus infinity. If you look at the equation for the unguided oval and change the hyperbolic cosine to a hyperbolic sine, then there is no restriction for y anymore. And what happens is you see this example, which is a non-compact, non-convex example, known as the Heraclid. Okay? So this is an example of an eternal solution because the solution exists for all time t in plus infinity as well. And as you let t go to plus infinity, everything converges to a horizontal line. Okay. Again, this solution, as you let t go to minus infinity, what you see around this point is Grim Reapers coming from above and Grim Reapers coming from below. Okay, so in the case of curve shortening flow, we know exactly what is happening with convex ancient solution. This is a theorem by Hamilton, Daskalopoulos, and Session that looked at compact convex ancient solutions. And I forgot to say this, but I'm always talking about embedded solutions. And they showed that there are only two examples, the shrinking circle and the unguided oval. Then we, together with Mat and Giuseppe, we were looking at this theorem, and we wanted to see also what happens in the case of non-compact flows. And it turns out that you only get two more examples, and that is the Grim Reaper and the stationary line. Something to mention here is that we use, so the original proof uses a lot of PDE methods, uses like this Lyapunov functional that has to say monotone under the flow. We used a more geometric, let's say, proof in the sense that we used the monotonicity formula of Huisken and Shuja-Wang's dichotomy, which we've seen, well, it has been mentioned in this conference already, but I'll say a little bit more in the next slide. Okay, and it turns out that this proof can be extended to include more flows, and we had actually showed that you can, in fact, have a similar classification with existence and uniqueness for curves moving by powers of the curvature, so kappa to the alpha, and you get uniqueness in the case where alpha is between 2/3 and 1, and you get an unguided oval for alpha between 1/2 and 1. Okay, so Shuja-Wang's dichotomy says that whenever you're looking at compact convex ancient solutions, then you can separate them into two big categories. The one is the ovaloids. These are solutions that sweep up all of space. And the other are pancakes. These are solutions that are confined between two parallel hyperplanes. So now we know a lot about the existence and uniqueness of these objects. So in the case of ovaloids, as Natasha mentioned before, there has been a description of the existence of a rotation symmetric guy by Brian White. Then Hasselhofer-Hershkovich gave a more detailed proof of this fact, and Anger and Daskalopoulos Session proved this precise asymptotic for the rotation symmetric example. For the pancakes, the existence of the pancakes was already known by Shuja-Wang, but then together with Mat and Giuseppe, we did a similar thing like the rotation symmetric ovaloid. We wanted to prove precise asymptotics of how this object moved in time. Okay, so what do we know like more on the uniqueness? As again, like just heard Natasha's talk, we know that there is a unique closed, non-collapsed, and uniformly two convex ovalloid that is not the shrinking sphere. And this is the rotational symmetric example. Right, and this two convexity is vacuous in 2 dimensions, and non-collapse, now we know that it's equivalent to being ovalloid. And for the what happens in the with the pancakes, well, we were able to show that if you just consider rotation symmetric ones, then you only have a unique one. And again, like here, to prove uniqueness, we used the fact that we were able to get precise asymptotics on how this pancake moves. But here, because things are confined between two parallel planes, to prove uniqueness, you can indeed use the Alexandrov reflection, okay? Because things are between two parallel planes, and you have a way to start your reflection. Okay, so I think like this is a big advantage of the pancakes compared to the ovalloids, is that you can use this reflection principle a lot easier. Okay, so after we constructed this rotational symmetric pancake, we wanted to ask the following questions. What are further examples of convex ancient solutions for n bigger or equal than 2? Okay, so for n equals 2, there's definitely not, you cannot look for more ovalloids, but there was evidence that there should be more pancakes. Okay, so this is the first thing. And then what about if you want to impose some boundary on your solutions? What can we say then about convex ancient solutions? And when you want to talk about mean curvature flow with boundary, like the natural way is to put free boundaries. So you have a hypersurface and you let your moving surfaces to hit that hypersurface orthogonal. Okay, so this is like the free boundary mean curvature flow. Okay, so these are the two questions I want to talk about in this talk. Okay, so together with the first question for looking for ancient solutions, if we think about the translating ones, remember the translating solutions are special examples of ancient solutions. They satisfy this equation that the mean curvature is equal to the normal dot a constant vector, and they move by translation. These are special examples of eternal solutions. Eternal solutions are solutions that live for all time in the past and for all time in the future. So we know that eternal solutions are non-compact. Eternal solutions are special cases of ancient ones, and translators are special solutions of eternal. So the question was, is the inverse true? And it was actually conjectured by Brian White that any convex eternal solution must be translated. So we also, in our attempt to construct more pancakes, we wanted to look at this question as well. Right, so how can you go about constructing more pancakes? An example would be this picture here. Okay, so you try to look at different translators and put them together. So this picture here shows 3 different wings. Okay, so these wings were also mentioned, I forget by who, but in this conference, these are solutions, translating solutions that live over slabs, and they're asymptotic to oblique green planes. Okay, so they have this reflection symmetry, they live over slab, and their width and angle have a certain relation. Okay, so you can think of trying to placing a lot of them together. So this was our first attempt. We wasn't extremely successful, but fortunately, very soon after, we realized that there is this interesting quantity that you can use to not only construct, but give some kind of classification of the pancakes. And this is what we call the squash down. So this omega star here. How is this defined? We take a solution MT, and let omega t be the region that it encloses. Okay, so mt is the boundary of omega t. So we take this omega t over t and take a limit as t goes to minus infinity. This produces a convex region, which we call omega star. So as an example, if we take the angular oval and we do this omega t over t, take a limit, the omega star will just be an interval -1 to 1. Okay, so here in this picture, because things are in slabs, the slab, as you go minus t, or sorry, over minus t, it will get squashed down. Okay, so you only see this one interval. For the pancake, because the pancake has displacement, so this is like t plus log t. So when I say t, I mean minus t. So, when you divide by minus t, you get 1 plus something that goes to 0. So here, again, you can compute the omega star, which is just the disk of radius 1. Okay, but again, we lose 1 dimension, and this is because we lose the part where the slab was. Okay, so this omega star is in a dimension lower than omega the omega t. Okay, so why does this squash down exist? This is not difficult to see if you use the support function. So the support function is the distance of the supporting hyperplane to 0. This we call sigma. And it turns out that sigma satisfies d sigma dt equals to minus mean curvature. Okay? And because of the Hamilton's Harnack inequality that says that the mean curvature is monotone under for an ancient flow, we get that sigma, this support function, is locally concave with respect to time. This local concavity plus Harnack inequality allows us to take limits both of the mean curvature and of this sigma over minus t. Okay, so and not only this, like if you look at this relation and the two monotonicities, what you get is the two limits are the same. Okay, so the limit of the mean curvature at a specific point with normal c as t goes to minus infinity has this value h star, and this is equal to the limit of the support function over minus t. So by looking at this, we get that the squash down omega star exists. And in fact, the sigma star is the support function of the squash down. Okay, so we want to analyze a little bit more the squash down, and the first observation one can see is the following. So we can look at an asymptotic translator for a specific z, so for a specific normal. That is the local behavior around this normal as t goes to minus infinity. Okay, so I take my surface, I look at the point where the normal is equal to z, I bring this point to the origin, and I let t go to minus infinity. So this, as we take this limit, this gives a translator. And this translator will move with speed h star. Okay, this h star of z should be here. Right, so now when we, let's suppose that the pancake that we're looking at lives in a slab of width pi, then of course the asymptotic translator also lives in a slab of width pi, but we know that such translators should move with speed at least 1, okay, because you can always use the Grimm plane as a barrier. So therefore, we already have that the support function of the squash down has to be at least 1. Or in other words, this means that the unit disk must be contained in the squash down. Okay, so now let's focus on ancient pancakes that live on a pi slab. And we're interested in the two following questions. Well, first, what omega star can occur as squash downs? And for what omega star can we construct solutions with this exact squash down? So for instance, again, like if we look at the pancake, we said that the pancake has omega star equal to the unit disk. So the unit disk is an example for which it does appear as a squash down, and there is indeed, we can construct a solution that has this guy as a squash down. The red guy is the example of the wings, okay, this translator that lives over a slab and is asymptotic to two oblique green planes. And this guy here, when we take the squash down, we're gonna see a circumscribed cone. Okay, so the squash down here looks exactly like a cone, and that circumscribes a disk of radius 1. Okay, so concerning the first question, for what omega star can we construct a solution? We have the following theorem. We know that there exists a convex ancient pancake, always in a pi slab, whose squash down omega star is equal to P for the following P's. So P will always be something circumscribed, and we can construct something for any regular polytope in dimension 2. Say we think of a regular polygon. It could be bounded or unbounded. P could be a simplex, again, like bounded or unbounded. And finally, a more weird example, P could be a truncated regular cone. Okay, so regular cone means that the length of the cone is a regular polygon or polytope, and we cut off, truncated means we cut off one vertex. So this last example, even though it doesn't seem that natural, it is interesting because it gives non-translating eternal solution, okay? And thus showing that White's conjecture is not true. Okay, these are solutions that are eternal but not translated. Moreover, all these solutions, the way we constructed them, they have a reflection symmetry. In their asymptotic translators, they do have the expected Gauss image. So this is probably a technical point, but I think it's interesting because this means that this picture here, where is it? This picture here was not that wrong. Okay, so these solutions we constructed, actually, when you take the asymptotic translators, you can find the wings. Okay, so let me give the rough idea of our construction. So we start by a polygon, P, which could be bounded or unbounded, but always circumscribed. Okay, so I'm going to call V the vertices and F the facets. But here, let's stick with dimension 2. Okay, so just think of a polygon. So I only have vertices and sides or faces, sides. Okay, so we start by this any such polygon, and we scale it by R. Okay, so meaning that I make now this circle inside of radius R. So now we go and attach green planes on each side. Okay, so in dimension, so I'm gonna go and attach green planes like this and like that on each side. Okay, the same with the compact and non-compact. And this creates something that is convex, of course, like it's not smooth, but we can flow it and create a mean curvature flow, which we call old but not ancient, okay, because it will live for longer and longer, but doesn't live for all time in minus infinity. And the idea is to look at these guys and take R to infinity and hope to obtain an ancient solution like that. Now there are these the very, very rough idea of why this works is because first, these solutions, that they are super solutions of the translator equation. So they satisfy this estimate, which stays true at later times. Okay, and this is true for any v. So v would be the v would be any vertex, and they satisfy mean curvature bigger or equal than normal dot v for any v. So they're a super solution for the translator equation. So this is more important estimate, and two more things are important. First, we can use the pancake as an inner barrier and the green planes as an outer barrier. So this is the very general sketch in the sense that you can imagine that the inner barrier allow you to say that the time goes to minus infinity. The outer barriers, they should somehow tell you that what you get is not just like two parallel planes, but of course, somehow you have to make sure that you get nice curvature estimates. Okay. And this is, the curvature estimates is the most like technical bit, because to do that, you have to do the following. So this is point 3. Okay, so just point 1 is what I said, that this h bigger than nu dot v stays true. You can do a maximum principle. You can do a width estimate that tells you that the limit would actually cover the whole width of the slab. And now for the curvature bound, you can use the fact that your solution satisfies h bigger than nu dot v, but the pancake satisfies the opposite estimate. And it does satisfy the opposite estimate away from its center. So you can use the pancake as an honest inner barrier in the sense that you can put it inside and you know that it's going to touch very close to its center, forcing your solution to have very small curvature. Okay. And this is how you get like a very nice estimate that says that if you are away from the edge is your polygon, then you have the mean curvature is bounded to the order e to the minus the distance to the, let's say, boundary. Okay, then you can do a similar trick using the pancake as an inner barrier to show that your squash down always has to be circumscribed. So now you have two things why we impose this condition. Symmetry, by saying that you have something regular, you impose some symmetry. And by saying that your P is simplex, you impose a minimality on the number of faces. And this ensures that your omega star is equal to P. Okay, so with the curvature estimate, everything you are able to take a limit, and then you want to prove that your limit has as omega star the P you started with. Well, the thing, because like omega star has to be circumscribed, and the symmetry or minimality of P cannot be anything else. Okay, so it has to be omega star. Right. Now, right, let me say something now more about what we know in general for this question. So if I take now any convex ancient pancake in a pie slab, and I look at this omega, this question, what could that be? So first, no matter what it is, you should always circumscribe Sn minus 1. So a picture like this here, this is inadmissible. Okay, it should have been like that, if anything. And moreover, when you have a Turner solution, you can do the same thing with time going to plus infinity. Okay, so you can take the same ratio, but now take t to plus infinity. And what you get a cone that you can obtain it by your omega lower star and placing your sides on the other side of the circle. Okay, just like the picture. So you see that every time you'll have a face like this would disappear. Okay, in the omega upper star. Now, why this is nice? Because we have like a few interesting applications. You can say that you get a translating solution if and only if the forward and backward squash downs are the same, which is if and only if the backward squash down is a convex. Okay, the forward one, it always is. We also can say that the solution is a green plane if and only if omega star is a half space. Okay? And in fact, this is the only, I'll say at the end, this is the only shape of omega star we know for which we can say that it determines the solution. And we also are able to show that all two-dimensional solutions, they are reflection symmetric, okay, with respect to the plane that separates the slab into two equal slabs. Okay, let me skip the sketch here so that we can say something about the free boundary as well. So the second problem I wanted to talk about is what happens for mean curvature flow with boundary. Okay, and as I mentioned, we'd say that we have free boundary mean curvature flow if our hypersurfaces, they intersect some given hypersurface sigma orthogonal. Okay, so if we look at the problem of classification of these solutions, we're gonna start with the easiest case, which is that of curves. Okay, so I'm gonna look at n equals 1, and I'm gonna look at a nice hypersurface S, in particular S1, okay, just a circle. And the theorem we have with Mat here is that there exists a unique non-trivial convex ancient solution with free boundary. Okay. Non-trivial meaning it's not just like the straight line or the segment. Okay. So this solution, moreover, it is reflection symmetric with respect to the y-axis. As time goes to 0, it goes to 0, 1. Okay, so it's a solution. Kind of looks like this. Disappears here at 0, 1. And as you go to minus infinity, it converges to the segment minus 1, 1 cross 0. And again, for this solution, we have nice asymptotics, which are given by this last, the third point, that say that if you look at your gamma as a graph, so this y would be the height, okay, so then we know that y is approximately like e to the lambda 0 squared t. Okay. And lambda 0 is a special number that satisfies this equation here. Okay. So y is exponentially small with time, and how small in the exponent of the exponential is given by lambda 0 squared, where lambda 0 satisfies this equation. Yeah, so let me try again to sketch the proof. So first, for the existence, we can start by any, we're gonna start by any curve that intersects S1. So let me just make a picture. So I'm looking here at, so this point here is cosine rho, comma sine rho. And I take any curve that intersects the circle orthogonally. I want it to be reflection symmetric with respect to the y-axis, and we want kappa to be increasing as you go to the boundary of the circle. Okay. Right, so we start with this curve, and now we let it flow by free boundary curve shortening flow. And it is known by work of Stahl that this solution would be convex, it will remain symmetric, and it will tend to 1, 0. Also, you can apply Sturm's theorem on the derivative of kappa that has only 1, 0, and say that it will still have only 1, 0 as time evolves. And this is because the derivative of kappa is equal to kappa at the boundary, which is positive. And moreover, you can use parts of circles as upper barriers to show that as you let rho go to 0, the time will go to minus infinity. So this is a good, this looks like a very good candidate to take rho to 0 and get your ancient solution. Okay, so these are the old but not ancient solutions. And this is indeed the case because you get very nice estimates. You can express this when you have a convex curve. There's a nice way you can express x and y in terms of the turning angle by the integral of cosine over kappa and sine over kappa. And by doing this, you get this nice estimate for the minimum and the maximum of the curvature. Here, my theta bar is, if you look at sometime t, theta bar is the maximum angle you see at the boundary. So you have this nice estimates for the curvature, and you have this height bounds. So here you will get the minimum of y, and here you get the sine of theta. Of course, you know that the sine of theta bar is bigger than the minimum, but you also know the other way with a constant. Right, and moreover, you have this, since theta bar moves, the speed of theta bar is equal to the maximum of the kappa, then you also get this nice bound on the maximum height. Okay, so all these estimates, they allow you to say that if you let rho go to 0, then you will get an ancient solution. Okay. And this estimate here is important because you know that your ancient solution is not going to be trivial. Okay, you have like something that goes to as time goes to minus infinity to the horizontal segment and goes to the point at the top as t goes to 0. Okay. Now, right. So what can we say about the uniqueness? For the uniqueness, the idea is the following. We want to show that this limit here exists. Okay, so this is a kind of like a nice estimate on y. So how does the height changes as time goes to minus infinity? So we want to say that it changes like e to the lambda squared t. So right. So we want to say that this exists, but it could be 0. And then we want to find a particular solution for which this is actually not 0. Okay, so we know that there is some solutions for which the y does move like e to the lambda squared t. Now, if we have this, then we can do our favorite trick that says that you can use these two solutions and the avoidance principle or the reflection principle. Here, it turns out the avoidance principle is enough to have uniqueness. Right. So, okay. So, in fact, if you have B, you can show that B implies A with this particular limit here as follows. So first, because of the avoidance principle, we know that any two solutions intersect. So we can take the random solution and scale it to create this sequence of solutions. And because our solution has to intersect this particular one, then we know that this limit exists. So we can take a limit as t goes to minus infinity and get a solution to a very simple equation for which we can do separation of variables and get what the solution looks like. So this is, again, like the rough idea, how if you know that a particular solution has this limit, then any other should as well. Right, and finally, what is this particular solution where this weird lambda 0 comes in is by taking pieces of the unguent oval. So if we take here, this guy's, so use the thing of, so if this is my circle, this is the center, then this unguent oval they're really big. They're almost like straight above zero. Okay, when we scale. Right. So we look at the scaled angular ovals, and you can check that for any angle theta here. So for any angle theta, you can find some scaled angular oval that passes through this point and intersect your circle orthogonally. And so this will be your initial curve. Now these guys with the specific lambda, immediately when you start with this guy, immediately will become a lower barrier because of the angle is going to hit the circle. And moreover, this lambda theta, as you let theta go to zero, it converges to a specific number, lambda zero, which is the one that we discussed at the beginning that satisfies this equation. Lambda zero times hyperbolic tangent of lambda zero. Okay, so these are the solutions you look at. This is a particular solution, and why this is nice, because for this you can prove that kappa over y here is very close to lambda zero square. Okay, so it's asymptotically equal to lambda zero square. And of course, like this takes a few maximum principle arguments, but I just want to like point out that the key thing here is, because you always have to be careful of the boundary, this was the correct quantity to look at for this particular solution, because kappa over y DDS is zero at the boundary. So you didn't have to worry about the boundary and do your standard maximum principles in the interior. Okay, so this is pretty much the very rough idea. Let me finish by saying what we didn't do. So first, we think that you can always construct in terms of the polygonal pancakes, you should be able to construct a solution for any circumscribed polygon. So we had this issue that, say, if you start by something like this, then when you do all this construction, maybe what you get is a triangle. Okay, so you might lose a face. For some reason, we couldn't come up with a nice way how to exclude this, but we still think it should be true. Then there is the interesting question of uniqueness. As I mentioned, the only squash down that determines on a one-to-one its solution is the straight line and the green plane. So it would be interesting to know if you have any kind of uniqueness. So even for omega star being S1, could we construct another solution? Like, of course, like if you assume rotational symmetry, then there's only the rotational symmetric pancake, but in general, it's not true. Or say, if you assume that omega star is a equilateral triangle, can you say that you only have one solution with a certain dihedral symmetry? Then there's the question of asymptotic translators, like this thing, asymptotic translator that I mentioned before. Do you get unique ones? Can you always determine them? Like it's unclear. Then maybe you can use this to have like an iterative construction of translators for higher dimension. And yeah, the last thing on the pancakes is that we also believe that the reflection symmetry should be true for any dimension, just like reflection symmetry in the midplane. Right, and for the free boundary problem, we are now looking to get estimates on the higher dimension of free boundary flow, where you have a hypersurface that intersects Sn. But I guess I should stop here.
Thanks, Theodora.
Can I ask a really dumb question? Is that okay? So Theodora, can you remind me, what are the boundary conditions for the free boundary for the mean curvature flow? Is it just orthogonal to the boundary? And you're always setting up as the sphere as what it's orthogonal to?
No. I mean, you can set other things. We just did the circle because this is the first time we're doing this free boundary, and it's what seemed to be the easiest.
Okay.
Yeah.
Thank you.
I think I've seen like with a plane or like with convex bodies.
Can I ask, so you have those eternal solutions that are not translators. Could you describe how do they look like geometrically?
They would look like, so I'm looking at this guy, right? So as you go backward in time, it would be like Grim Reapers like this, Grim Reapers here, Grim Reapers there. But as you go forward in time, this will become a...
Maybe the picture with
There's like two flying wings that hit each other and combine into one, is that?
Yeah, exactly. Yeah, forward in time, it will have, because it's the cone, it will have to look like the wing. But backward in time, it kind of like, so if at any point you would see a translating Grim plane, but this translating Grim plane changes.
Maybe it would help if you could tell me what is omega lower star and what is omega upper star.
Yeah, this would be the omega lower star, right?
Okay.
And the omega upper star would be this.
That's right. So the exterior angles are preserved here.
Okay, got it. Thanks.
Here, say we had this question when I say about the asymptotic translators, like Ben said, is it two wings that come together, or is it like maybe different or green planes?
Didn't we show that in the two-dimensional case you do get the wings in higher dimensions? It's unclear, isn't it? Is that right?
In two-dimensional case, yeah, I think we showed that you have only it's only the wings. It cannot be. No.
Yeah, it's actually quite hard to show that at the vertices you really always get a wing, or you might just get thin Grim hyperplanes slowly changing direction.
Yeah,
I think we conjecture that that doesn't happen.
Well, actually, also in this case, because we constructed them and we have like the width estimate, then these are wings. The ones
right, for the constructed ones, yeah.
Just a quick one, whether anyone's found these kinds of solutions for Ritchie flow yet. I mean, I know there's the flying wings, but these more complicated ones probably exist, right?
Yeah, I just know about this like the wings.
Yeah.
There's a lot of things that come from like homogeneous constructions, so it's a lot more complicated. But these exact analogs of these don't seem to be constructed, as far as we could work out in a couple of days last week. But maybe other people know better.
Yeah, I guess you can't just take the intersection, can you?
No.
I was just going to ask whether you've thought about the free boundary problem, say in a convex body in the plane, for example. Can you classify the ancient free boundary things in that situation?
We have said that we should look at this. That's the development there.
Okay, good. Seems a natural question.
But like, say if it is something, I think like that is symmetric, also like an ellipse, maybe it would be easier to do similar things.
I think a lot of stuff we do carries over, but there's one or two things that are going to be a bit tougher.
So is it plausible to say that your ancient things should always start at a straight line meeting the boundary orthogonally and ends up at a round semicircle on the boundary, I guess? Is that
I think this is part of the work of Stahl. I think he shows that he didn't look at ancient solution, but at least like the forward thing.
Yeah,
that it goes
sure,
to
no, that
something.
part is, of course, it's known, yeah.
Yeah.
But I guess it's the unique. I guess for each straight line you can find, then I guess that meets the boundary at the right way. Then there should be exactly two solutions starting from that. I guess.
I think that's probably right if under even bounded length assumption, like the Choi Mentalitis work. Yeah. But maybe there exist solutions with unbounded length. That would be nice to see. I've got a question for Bob, if I might. Whether the picture, so the solutions you construct with, I think, is it Winkoi, if it is a sort of similar picture to what we're getting here with the squash downs.
So I mean, what we did, it's like a compact version of those Hoffman, Ullmann, and Martin White solutions. So you have ellipsoid that they kind of look like ellipsoids, but then it's not the case that all long axes have exactly the same length, but you can prescribe the ratio between them. Yeah, so we only did it in the non-collapsed case because that's the case we were most interested in. But probably if you do it in the collapsed case, then you I guess you could get non-uniqueness even when the squash down is.
Yeah, so you think the squash down would be the round disk, right? That would be
Yeah,
right.
I think that the squash down will always you prescribe the ratio between those axes, but for time going to minus infinity, all those ratios become equal to 1.
And that's the case for the translators. The squash down is just the line. Is that right? For all of those examples.
Oh, those examples are compact examples. So that's.
Sorry, I meant for the Hoffman, Illman, and Martin line examples.
So that the blowdown of a time slice, I think, is always just a half line.
That's right. Yeah. Thanks very much. Cool. Thanks very much, Theodora.